Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is Phasor representation of electrical quantities. Our objective is to learn how to represent sinusoidal electrical phenomenon like voltage and current using Phasor notation. This lecture operates under the presumption the viewer has more than a passing familiarity with both time-variant sinusoidal phenomenon and complex numbers. If you lack this level of familiarity, by all means revisit and review the preceding lectures until you are so qualified. Today we'll learn to simplify sinusoidal expressions using Phasor notation, a technique developed by one Charles Proteus Steinmetz, a personal hero of mine. Prior to Steinmetz's influence, AC circuit theory and analysis necessitated complicated, time-consuming calculus-based methods. His work with complex numbers, vectors, and phasors, however, made it possible to arrive at these same results using simple algebraic techniques. For this, we thank you, Charles Proteus Steinmetz, and are forever in your debt. Let us begin. Numerous features characterize sine waves, among them peak values, peak-to-peak values, effective values, instantaneous values, frequency, period, and phase shift. Let's thin this unruly mob to only those properties essential to our discussion and toss the rest of these lazy moochers overboard. Of these properties, 3 stand out as the most useful and informative, from which all other properties can be derived. These properties are the effective value, the frequency, and phase shift. Given sinusoidal voltage input results in sinusoidal current output of the same frequency, even the utility of frequency is questionable. We're not willing to chuck frequency entirely overboard, however, we are at least willing to push it off the deck and let it cling to the rails. We are left with the effective value and phase shift. Phasor notation is a means of compressing a sinusoidal phenomenon into a readable shorthand using only these 2 properties. The Phasor representation of a sinusoidal phenomenon is something akin to polar format, where the effective value is the magnitude and the phase shift is the direction. At first, the act of simplifying a time-variant sinusoidal expression into something akin to a complex number might seem incongruous. However, recall from the sine waves lecture, available at the Big Bad Tech channel, that the origin of the sine wave itself is rooted in circular rotation. It can be visualized as the height of a point traveling a circular perimeter of a given radius above or below the horizontal axis. The phase shift determines the angular amount by which this analysis is shifted. It makes sense then that something with a magnitude and direction, in this case a complex number in polar format, can be used to compactly represent this phenomenon. Allow me to demonstrate the utility of Phasor notation. Consider time-variant sinusoidal voltage with the following expression. V of t equals 33.9 volts times the sine of 360 times 60 times t plus a phase shift of 0 degrees. And time-variant sinusoidal current with the following expression. I of t equals 17 milliamperes times the sine of 360 times 60 times t minus a phase shift of 20 degrees. Using our previously developed skill set, we could spend our time calculating various properties of these waveforms, including, but not limited to, painstaking instantaneous analysis. However, given the repetitive nature of sine waves, the utility of this technique is somewhat questionable. Additionally, we can plot these waveforms on the same graph. However, it quickly becomes busy and unreadable. A far easier means of representing and manipulating these same sinusoidal waveforms is through the use of Phasor notation. The voltage waveform has an effective value of approximately 24 volts, and its phase shift is 0 degrees, meaning it is our reference. Our Phasor representation of voltage is V equals 24 volts at an angle of 0 degrees. The current waveform has an effective value of approximately 12 milliamperes, and is phase shifted negative 20 degrees, meaning it lags our reference voltage by 20 degrees. The Phasor representation of current, I equals 12 milliamperes at an angle of negative 20 degrees. When viewed on a phasor diagram, the voltage phasor has a magnitude of 24 volts and is pointed at 0 degrees, and the current phasor has a magnitude of 12 milliamperes pointed at negative 20 degrees. Note the Phasor representation of voltage and current are both written using capital letters and include an overbar, indicating this is a complex number with both magnitude and direction. It is immediately evident the relationship between voltage and current without sorting through a tangled mess of time-variant equations, properties of dubious utility, nor confusing graphs. Phasor notation strips down a heavy sine wave into only its most essential properties, the effective value and the phase shift, essentially the magnitude and direction of a complex number expressed using polar format. It should be noted that frequency is still with us, and that this phasor diagram is only relevant at our current given frequency of 60 Hz, the simplicity being that both voltage and current are assumed to have the same frequency. Phasor notation, in addition to compactly representing important electrical properties, is also a means of illustrating a plot of these properties in as small a space as possible. As I previously mentioned, the origin of a sine wave itself is rooted in circular rotation and can be visualized as the height of a point traveling a circular perimeter of a given radius above or below the horizontal axis. The phase shift determines the angular amount by which this analysis is shifted. If we were to multiply the effective values by square root 2 and then rotate the voltage and current phasors on our phasor diagram in the counterclockwise direction, voltage would describe a sinusoidal path with no phase shift, and current would describe a sinusoidal path with a negative 20-degree phase shift, meaning it lags voltage by 20 degrees. In summary, time-variant sinusoidal phenomenon can be more efficiently represented using phasor notation, where phasor notation is something quasi-equivalent to a complex number expressed in polar format, being the effective value, the magnitude, and the phase shift, the direction. Let's try a couple illustrated example problems about phasor representation. Our first illustrated example problem shows a plot of voltage and current. Let's first determine the time-variant expressions of these sinusoidal phenomenon, then determine their equivalent phasor representations. Voltage appears to have a peak value of 170 volts and a period of approximately 16.7 milliseconds. A period of 16.7 milliseconds corresponds to a frequency of approximately 60 Hz. We're not given a phase shift for voltage, but let's assume it's our reference at 0 degrees. If we wanted to write the time-variant expression for this sinusoidal voltage, it would be V of t equals 170 volts times the sine of 360 times 60 times t plus 0 degrees. The real estate and time involved in expressing this in the time domain could be put to better use using phasor notation. A peak of 170 volts corresponds to an effective value of approximately 120 volts. Voltage expressed in phasor notation is equal to 120 volts at an angle of 0 degrees. Which would you rather drag around all day, the time-variant expression or the light and nimble phasor format? I know which one I'd choose. Let's do the same for current. Current appears to have a peak value of 425 milliamperes. It also appears to have a period of 16.7 milliseconds. However, it seems to be shifted 4 milliseconds in advance of voltage. Despite the phase shift, current still has a period of 16.7 milliseconds and therefore has the same frequency of 60 Hz. Given 4 milliseconds inside a 16.7 millisecond period represents approximately 24% of this period, this represents a positive phase shift of 24% of 360 degrees, or approximately positive 86.4 degrees. If we wanted to write the time-variant expression for the sinusoidal current, it would be I of t equals 425 milliamperes times the sine of 360 times t plus 86.4 degrees. A peak value of 425 milliamperes corresponds to an effective value of approximately 300 milliamperes. Current expressed in phasor notation is equal to 300 milliamperes at positive 86.4 degrees. Again, which format would you rather drag around all day? The time-variant expression or the light and nimble phasor format? The choice should be obvious. In addition to efficiently representing these quantities that most matter to AC circuit analysis, effective value and phase shift, note the phasor diagram of these two properties additionally represents the phase relationship far more compactly and more obviously than can the time domain plot. It is immediately evident that current leads voltage by 86.4 degrees without the heartbreaking toil of calculation, nor the very real possibility of dorking it up. Let's try this in reverse. Let's say we're given the following phasor diagram and asked to represent these quantities using the time domain and then graphically illustrate these phenomena in the same plot. The phasor representation of voltage makes it clear voltage has an effective value of 48 volts at negative 15 degrees. The phasor representation of current makes it clear current has an effective value of 100 milliamperes at positive 20 degrees. Additionally, note the phasor diagram makes it very obvious that current leads voltage by 35 degrees without the use of heavy calculations nor any technique subject to interpretation errors. all you have to do is look at the phasor diagram and this relationship is immediately evident. There is a relative phase shift of 35 degrees, where current leads voltage by 35 degrees. I'll come back to this point in a moment. Let's transition these phasor representations to the time domain. Note the phasor diagram indicates these properties are valid at 40 Hz, which corresponds to a period of 25 milliseconds. Given an effective value of 48 volts, the peak value of voltage is approximately 67.9 volts. Given an effective value of 100 milliamperes, the peak value of current is approximately 141.4 milliamperes. Voltage expressed in the time domain is therefore V of t equals 67.9 volts times the sine of 360 times 40 times t minus 15 degrees. Similarly, the current expressed in the time domain is I of t equals 141.4 milliamperes times the sine of 360 times 40 times t plus 20 degrees. If we were to plot voltage, note the voltage waveform would lag our established reference by 15 degrees. Given 15 degrees is 1/24th of 360 degrees, this represents a backward shift of 1/24th of our 25 millisecond period, or approximately 1.04 milliseconds. If we were to plot current, note current leads our established reference by 20 degrees. Given 20 degrees is 1/18th of 360 degrees, this would represent a forward shift of 1/18th of our 25 millisecond period, or approximately 1.39 milliseconds. Given this phase-shifted response, current appears to be leading voltage by a relative 2.43 milliseconds, where this relative 2.43 millisecond shift represents a differential of current leading voltage by 35 degrees. Take a moment to appreciate what just occurred. Note the copious amount of both time and real estate the time domain necessitated to convey and depict the same properties the phasor diagram did in 1/100th of the time and space. It is for this reason alone the phasor format is preferred over the time domain. But wait, that's not all. In addition to simplifying the representation of sinusoidal electrical phenomenon, phasor format has other uses as well. The true utility of phasors will only become apparent in later lectures detailing their use, but as a preview, consider this seemingly simple problem and its rather complex solution. What's a sine wave plus a sine wave? The simple answer is another sine wave. However, the complexities lie in determining the properties of the resultant sine wave. By way of an analogy, the act of adding sine waves might be equivalent to the act of watching tidal influences or wind-driven waves coming in and out of a harbor. The instantaneous values of two separate waves combine such that it results in a single waveform that is a mixture of the effects. For example, given a waveform 1 represented in the time domain as V1 of t equals 20 volts times the sine of 360 times 60 times t plus 12 degrees, and waveform 2 represented in the time domain as V2 of t equals 30 volts times the sine of 360 times 60 times t plus 28 degrees, and we're being asked to add them together. V1 of t plus V2 of t equals V single prime of t. Note these waveforms have the same frequencies, only their peak values and phase shifts differ. One could perform tedious instantaneous analysis to determine the resultant waveform, or resort to any number of trigonomic properties, which I'm certain you don't remember despite having taken a 12-week trigonometry course, or more simply, convert the waveforms to the phasor domain and simply add them together. V1 has an effective value of 14.1 volts. Therefore, V1 expressed in the phasor domain is 14.1 volts at an angle of positive 12 degrees. V2 has an effective value of 21.2 volts. V2 expressed in the phasor domain is 21.2 volts at an angle of positive 28 degrees. Now all we need to do is add them up as complex numbers expressed in polar format using our scientific calculator. V1 plus V2 equals V single prime. V single prime equals 35 at an angle of positive 21.6 degrees. The phasor diagram clearly indicates V single prime to be the summation of V1 and V2 phasors. It is also immediately evident that V single prime has an effective value of 35 volts and is phase shifted positive 21.6 degrees in advance of our previously agreed upon reference. Problem solved without heartbreaking labor, nor cracking open a dusty old trigonometry textbook, all thanks to Phasors and Charles Proteus Steinmetz for having the foresight to apply this technique to AC circuit analysis. If you wanted to, you could convert V single prime to the time domain and plot it. V single prime with an effective value of 35 volts has a peak value of 49.5 volts. Given this phasor diagram is known to be relevant at 60 Hz, V single prime of t equals 49.5 volts times the sine of 360 times 60 times t plus 21.6 degrees. Plotting V1 of t, V2 of t, and their summation V single prime of t on the same graph yields nothing short of a hot mess. Yes, if you took the time and effort to stare at this without blinking for a couple hours, you should be able to see how the instantaneous values of V1 plus V2 add up to yield V single prime, but ain't nobody got time for that. The phasor diagram clearly and quickly shows you that V single prime is a summation of V1 and V2 without any toil nor confusion. The resultant effective value and phase shift are readily apparent with minimal calculation. We'll examine the utility of phasors in later lectures on AC Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. Until then, let's close out this lecture with a couple example problems. Put your understanding of phasor representation of time-variant sinusoidal electrical phenomenon to the test with these example problems. Since these techniques necessitate attention to detail, let's go through them one by one. The first example shows a plot of voltage as a function of time. It looks to have a peak value of 78 volts. The separation between the two zero crossings going positive appears to be 20 milliseconds. And finally, it looks like the first zero crossing going positive appears to lead our previously agreed upon reference by 2 milliseconds. See if you can express this voltage waveform as a time-variant expression and again as a phasor equivalent. Finally, draw the phasor equivalent on a phasor diagram. By all means, pause the lecture and attempt to solve the desired properties on your own. If you're tracking, you should have obtained the following results. Given a period of 20 milliseconds, this waveform has a frequency of 50 Hz. Given this waveform is leading our previously agreed upon reference point by 2 milliseconds, this corresponds to a phase shift of positive 36 degrees. Therefore, this waveform has a time-variant voltage expression of V of t equals 78 volts times the sine of 360 times 50 times t plus 36 degrees. This peak value corresponds to 1 over square root 2 of 78 volts, or 55.2 volts. The phasor equivalent of V is therefore equal to 55.2 volts at an angle of positive 36 degrees. Illustrated in the phasor diagram, V is a magnitude of 55.2 volts and is pointed at an angle of positive 36 degrees. Let's try a similar example problem. The second example shows a plot of current as a function of time. It looks to have a peak value of 390 milliamperes. It looks to have a period of 20 milliseconds. This is the same value observed in the first example problem, so it should probably have the same frequency. Hint, hint. Finally, it looks like the first zero crossing going positive appears to lag our previously agreed upon reference by 3 milliseconds. As previously, see if you can express this current waveform as a time-variant expression and again as a phasor equivalent. Finally, draw the phasor equivalent on a phasor diagram. By all means, pause the lecture and attempt to solve for the desired properties on your own. If you're tracking, you should have obtained the following results. Given a period of 20 milliseconds, this current waveform has a frequency of 50 Hz. Given the waveform is lagging our previously agreed upon reference by 3 milliseconds, this corresponds to a phase shift of approximately negative 54 degrees. Therefore, this current waveform is a time-variant expression of I of t equals 390 milliamperes times the sine of 360 times 50 times t minus 54 degrees. This peak value corresponds to an effective current value of approximately 275.8 milliamperes. The phasor equivalent I is therefore equal to 275.8 milliamperes at an angle of negative 54 degrees. Illustrated on the phasor diagram, I has a magnitude of 275.8 milliamperes and is pointed at an angle of negative 54 degrees. Going back to our first example problem examining a voltage waveform with the same frequency, we can compare and contrast the two methods of representing electrical phenomena. The time domain representation of voltage and current is a little messy. Would necessitate some serious effort on your part to determine the effective value and phase shift for each property, and the relative phase shift between them. This being said, it's still possible, but not a task to be undertaken lightly. The phasor representation, in contrast, is substantially easier to interpret. it is immediately evident voltage has an effective value of 55.2 volts. Current has an effective value of 275.8 milliamperes. Voltage leads our established reference by 36 degrees. Current lags our established reference by 54 degrees. And finally, the relative phase shift of current with respect to voltage shows that current lags voltage by 90 degrees. In summary, phasor representation conveys as much usable information as possible in as little space as possible by ditching all the noise. If I haven't yet convinced you about the utility of phasor notation, you will be after this one. Our third example problem shows you what a tangled mess the time domain can be and how the phasor domain can present more pertinent information in a much smaller package. A plot of voltage and current as a function of time appear on the same graph. Let's say we're being asked to express voltage and current as phasor equivalents. It looks like voltage has a peak value of 7.4 volts, and current has a peak value of 15.8 milliamperes. Both voltage and current appear to have a period of 15 milliseconds. Looks like the first zero crossing going positive for voltage appears to lag our previously agreed upon reference by 1.2 milliseconds. And it looks like the first zero crossing going positive for current appears to lead our previously agreed upon reference by 2 milliseconds. See if you can express both voltage and current as phasor equivalents, and draw the phasor equivalents on a phasor diagram. Finally, see if you can use the phasor diagram to determine the relative phase shift between voltage and current. Does current lead or lag voltage, and if so, by how much? By all means, pause the lecture and attempt to solve for the desired properties on your own. If you're tracking, you should have obtained the following results. We don't necessarily need to solve for frequency, since we're not being asked to solve for the time domain expression of voltage or current, but rather the phasor equivalent. However, should the need arise, given a period of 15 milliseconds, both waveforms have a frequency of approximately 66.7 Hz. Given a voltage peak of 7.4 volts, this corresponds to an effective value of approximately 5.2 volts. Given voltage appears to lag our previously agreed upon reference by 1.2 milliseconds within a period of 15 milliseconds, this corresponds to a phase shift of negative 28.8 degrees. The phasor equivalent of voltage is therefore equal to 5.2 volts at an angle of negative 28.8 degrees. Illustrated in the phasor diagram, V has a magnitude of 5.2 volts and is pointed at an angle of negative 28.8 degrees. Given a peak current value of 15.8 milliamperes, this corresponds to an effective current value of 11.1 milliamperes. Given current appears to lead our previously agreed upon reference by 2 milliseconds within a 15 millisecond period, this corresponds to a phase shift of positive 48 degrees. The phasor equivalent of current is therefore equal to 11.1 milliamperes at an angle of positive 48 degrees. Illustrated on the phasor diagram, I has a magnitude of 11.1 milliamperes and is pointed at an angle of positive 48 degrees. Additionally, the phasor diagram makes it clear that there's a relative phase shift of positive 76.8 degrees between current and voltage, and that current leads voltage by 76.8 degrees. Which diagram would you rather use? The choice by now should be obvious. Let's try this in reverse. Our fourth example problem shows a phasor diagram with V voltage being equal to 42 volts at an angle of positive 10 degrees, and I current being equal to 20 milliamperes at an angle of positive 30 degrees. We're being asked to determine a very simple property. What's the relative phase shift between voltage and current? Does current lead or lag voltage, and if so, by how much? This should be the easiest of tasks in the phasor domain. To make this a worthy example problem, let's complicate it ever so slightly. Additionally, we're being asked to express voltage and current in the time domain with the understanding that our phasor diagram is valid at a frequency of 120 Hz. Finally, we're being asked to plot both the voltage and current waveform in the same graph and measure the relative phase shift between them. This won't be nearly as easy as using the phasor diagram. By all means, pause the lecture and attempt to solve for the desired properties on your own. If you're tracking, you should have obtained the following results. Using the phasor diagram, it makes it immediately clear that there's a relative phase shift of 20 degrees between current and voltage, and that current leads voltage by 20 degrees. There is no arduous calculation nor toil about it. If only the same thing could be said about the time domain. A frequency of 120 Hz corresponds to a period of approximately 8.3 milliseconds. Given an effective value of 42 volts, this corresponds to a peak voltage value of approximately 59.4 volts. The time domain expression of voltage is therefore V of t equals 59.4 volts times the sine of 360 times 120 times t plus 10 degrees. Given voltage is phase shifted by positive 10 degrees, this corresponds to a time shift of approximately 231.5 microseconds as this operation illustrates. If we were to plot the voltage waveform, note it peaks out at 59.4 volts. The two zero crossings going positive are separated by approximately 8.3 milliseconds, and the waveform appears to be shifted approximately 231.5 microseconds in advance. Now let's do the same thing for current. Given an effective value of 20 milliamperes, this corresponds to a current peak value of approximately 28.3 milliamperes. Time domain expression of current, I of t, is equal to 28.3 milliamperes times the sine of 360 times 120 times t plus 30 degrees. Given current is phase shifted by 30 degrees, this corresponds to a shift of approximately 694.4 microseconds as this operation illustrates. If we were to plot the current waveform and note it peaks out at approximately 28.3 milliamperes, it has a period of approximately 8.3 milliseconds, and the waveform appears to be shifted approximately 694.4 microseconds in advance of our previously agreed upon reference. Using solely the time domain, you will note that there is a relative time shift of 463 microseconds between voltage and current, which corresponds to a relative phase shift of positive 20 degrees, meaning current leads voltage by 20 degrees as this operation illustrates. Isn't that the same result we obtained just by looking at the phasor diagram? Yes, it is. And note, looking at the phasor diagram took far less effort than digging through all this garbage to arrive at the same result. In summary, phasor equivalents present far more usable information in a much smaller package. I rest my case. Let's try this in reverse. Our fourth example problem shows a phasor diagram with V voltage being equal to 42 volts at an angle of positive 10 degrees. And I current being equal to 20 milliamperes at an angle of positive 30 degrees. We're being asked to determine a very simple property. What's the relative phase shift between voltage and current? Does current lead or lag voltage, and if so, by how much? This should be the easiest of tasks in the phasor domain. To make this a worthy example problem, let's complicate it ever so slightly. Additionally, we're being asked to express voltage and current in the time domain with the understanding that our phasor diagram is valid at a frequency of 120 Hz. Finally, we're being asked to plot both the voltage and current waveform in the same graph and measure the relative phase shift between them. This won't be nearly as easy as using the phasor diagram. By all means, pause the lecture and attempt to solve for the desired properties on your own. If you're tracking, you should have obtained the following results. Using the phasor diagram, it makes it immediately clear that there's a relative phase shift of 20 degrees between current and voltage, and that current leads voltage by 20 degrees. There is no arduous calculation nor toil about it. If only the same thing could be said about the time domain. A frequency of 120 Hz corresponds to a period of approximately 8.3 milliseconds. Given an effective value of 42 volts, this corresponds to a peak voltage value of approximately 59.4 volts. The time domain expression of voltage is therefore V of t equals 59.4 volts times the sine of 360 times 120 times t plus 10 degrees. Given voltage is phase shifted by positive 10 degrees, this corresponds to a time shift of approximately 231.5 microseconds as this operation illustrates. If we were to plot the voltage waveform, note it peaks out at 59.4 volts. The two zero crossings going positive are separated by approximately 8.3 milliseconds, and the waveform appears to be shifted approximately 231.5 microseconds in advance, previously agreed upon reference. Now let's do the same thing for current. Given an effective value of 20 milliamperes, this corresponds to a current peak value of approximately 28.3 milliamperes. Time domain expression of current, I of t, is equal to 28.3 milliamperes times the sine of 360 times 120 times t plus 30 degrees. Given current is phase shifted by 30 degrees, this corresponds to a shift of approximately 694.4 microseconds, as this operation illustrates. If we were to plot the current waveform and note it peaks out at approximately 28.3 milliamperes, it has a period of approximately 8.3 milliseconds, when the waveform appears to be shifted approximately 694.4 microseconds in advance of our previously agreed upon reference. Using solely the time domain, you will note that there is a relative time shift of 463 microseconds between voltage and current, which corresponds to a relative phase shift of positive 20 degrees, meaning current leads voltage by 20 degrees, as this operation illustrates. Isn't that the same result we obtained just by looking at the phasor diagram? Yes, it is. And note, looking at the phasor diagram took far less effort than digging through all this garbage to arrive at the same result. In summary, phasor equivalents present far more usable information in a much smaller package. I rest my case. Last problem before I let you go. Consider a digital multimeter in AC voltmeter mode displaying a reading of roughly 4.5 volts. And we're being instructed to assume this is the reference waveform and place it in phasor format. By all means, pause the lecture and attempt this on your own. If you're tracking, you should have obtained the following result. Our task could not be any easier as long as you realize all AC voltmeters, all the time, always display effective or RMS voltage unless explicitly stated otherwise. This digital multimeter is displaying an effective or RMS voltage value of roughly 4.5 volts, and it is the reference waveform. The phasor equivalent is therefore 4.5 volts at an angle of 0 degrees. Do we care about frequency? No, we don't. We're in the phasor domain, and we can just assume that everything has the same frequency, whatever it might be. The same thing can be said about ammeters. All AC ammeters, all the time, always display effective or RMS current unless explicitly stated otherwise. What about phase shift? Does a digital multimeter in voltmeter or ammeter mode display phase shift? No, they don't. Voltmeters and ammeters ordinarily do not measure phase shift, but rather restrict themselves to the measurement of effective voltage and current magnitude only. This is to imply that the digital multimeter can only give a user partial information about the true nature of AC circuits. We'll examine the means one uses to experimentally determine phase shift using an oscilloscope in the very near future. Alright, hopefully you did well on that example set. Really, there's not much more to discuss about phasor equivalents given we've already spent ample amount of time discussing peak and effective values, period and frequency, and phase shift in previous lectures. All you've got to do to reliably convert between the time domain and phasor equivalent and vice versa is to apply these previously mastered techniques and have a modicum of organization. Again, the phasor representation of time-variant sinusoidal phenomenon is quasi-equivalent to a complex number using polar format, where the magnitude is the effective value, not the peak value, the effective value, and the direction is the phase shift. We'll examine more applications of phasors in later lectures. Until then, this concludes this lecture. In conclusion, this lecture examined the means of representing time-variant sinusoidal phenomenon as phasors. Phasor notation is quasi-equivalent to a complex number using polar format, where the magnitude is the effective value and the direction is the phase shift. Phasors make it possible to compactly convey the most pertinent information about sinusoidal phenomenon in the smallest possible amount of space and time. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.